Exercise 940 introduces you to a type of question that will become more and more common as organic chemistry progresses. It's a synthesis question, and it is sometimes one of the harder question types because it requires you to have already memorized sometimes large amounts of information, for example, all of the recipes in this chapter, and also to remember substitution and elimination reactions. But it's ultimately the goal of organic chemistry. The goal is to turn you into something in between a magician and a chef, in order to take some molecule that maybe is toxic or really inexpensive and turn it into a medicine that you can use to help humanity and start a business or make money off of. So it's our goal, and so we're gonna have a healthy dose of it, but it is one of the more difficult problem types. And so from this video on, in this chapter, for this exercise and the other exercises that do a similar thing, where they give you a reagent, they give you a product, and they ask you, how do you make that happen? In these exercises, I have to assume that you have memorized the reactions already. There's no way to do these exercises without having memorized the recipes. And so these hopefully will give you some exercise with thinking through those recipes once you have those memorized. So if you're trying to watch this before you have them memorized, this may not help you that much. But if you have them memorized already, this will hopefully guide your thinking in navigating that information. Okay, so let's get started. It says, identify the reagents you would use to accomplish each of the following transformations. So you know what you have, you know where you want to go. The question is, how do you get there? Now we're going to start off with just one step syntheses. Okay, we see that we have an alkene. So instantly we should be thinking, probably this is an addition reaction. You see that the double bond goes away as you go from left to right. So what are we adding? Well, look for things that are there in the products that are not there in the reagents. Here we see this OH kind of stands out. That's not there in the reagents. Now there's another thing. This carbon here has only 3 bonds drawn explicitly. Here it has 4 bonds drawn explicitly. That means that there is one other bond there that's not drawn explicitly. That can only be to a hydrogen. Okay, so we see the two things that we added. We added an H and an OH. There are 3 ways that you know how to add an H and an OH. There's acid-catalyzed hydration. That will add an H and an OH in a Markovnikov way, so the H will go to the less substituted carbon, and it will be, you could have rearrangement, because you form that carbocation intermediate, so it could rearrange. So that's one option. A second option, a second way of adding H and OH is oxymercuration demercuration. Now with oxymercuration demercuration, you also get Markovnikov addition. So in that way it's similar to acid-catalyzed hydration. The H will go to the less substituted carbon, but in this case you don't get rearrangement. And there is a third way that we know of adding H's and OH's. So first is acid-catalyzed hydration, second oxymercuration demercuration. The third way is hydroboration oxidation. And that recipe will add the H and the OH anti-Markovnikov. That means that's the only way you can add an H and an OH anti-Markovnikov. That means that the H will go to the more substituted carbon. And the other thing you want to remember about that is its syn addition. And you don't have to worry about rearrangement there. Okay, so we see the H and the OH. Let's think about the 2 carbons that they're on. We can decide whether it's Markovnikov or anti-Markovnikov addition. The carbon that has the hydrogen on it is bonded to 1, 2, 3 other carbons. So that is tertiary. The carbon that has the OH on it, that's bonded to 1, 2 other carbons. So that is secondary. Notice that the H went on the more substituted carbon. That is anti-Markovnikov addition. In anti-Markovnikov addition, the H goes to the more substituted carbon. In Markovnikov addition, the H would go to the less substituted carbon. Here, the secondary one. So we know the addition has to be anti-Markovnikov, and that means our only option here is hydroboration oxidation. So it has to be hydroboration oxidation that you would do to get this transformation to happen. So the recipe you would need to add is, first, you would add borane, BH3, or you could also add 9-BBN. Those are both options. Remember, the 9-BBN is a solid, which is nice because borane is a gas, and these compounds are pretty toxic, so it's better to deal with a solid than a gas. But you could use borane or 9-BBN, stabilized by tetrahydrofuran. That's using its lone pairs on the oxygen of that. Remember, tetrahydrofuran looks like this. You use those lone pairs to stabilize the empty p orbital in the boron. So that's one step, followed by, so this adds the hydrogen in the boron, so hydroboration, followed by hydrogen peroxide, and it's going to be one of the OHs on the hydrogen peroxide that replaces the boron, so that's the oxidation step, and to activate that, you use sodium hydroxide. So the answer for this question is this recipe. This is what you would add in order to make that transformation happen. Okay, let's make this a little smaller so it doesn't clutter up our space quite as much. Okay, we go to the second one. Now, in this example, we see a bromine that's there in the reagent and it is not there in the product. Also, if you notice, we have a double bond that's forming. Now this hydrogen here would have this carbon here would have 3 hydrogens on it. This only has 2. So we're also losing a hydrogen. Right, that's not really there. This one is not really there anymore. So we're losing an H and a Br. And this is an elimination reaction. Elimination reactions are where you have a leaving group that's there and then it's not there anymore, and you form a double bond. So I'm going to erase these H's so that they don't clutter up our space. But we're doing an elimination reaction, so we have a leaving group and the beta hydrogen that's going to kick that off. Okay, well, what you need to add for an elimination reaction is a base. That's what you need. But there are different types of bases. You could have a skinny base or a bulky base. Which one do you need here? Well, let's imagine if we go back to our molecule, there are the position where the alpha carbon is, the position where the leaving group is, that's the alpha carbon. Each carbon bonded to that is the beta carbon. Now notice these positions here are really the same. They're symmetrical. They're both methyl groups attached to the alpha carbon, and so they'll react in the same way, so I'm only going to consider one of those. You could take the beta hydrogens, the hydrogens off of those beta carbons, you could take either of those and get 2 different products. On the one hand, a base can come in and steal this beta hydrogen, the electrons, so that base would steal a hydrogen, the electrons would go toward the leaving group and kick the leaving group off. And in that case, you would have the double bond form toward the beta hydrogen that you stole. On the other hand, you could imagine a base coming in. Well, let me keep this here. You can imagine another base coming in. And the base could steal the other beta hydrogen. The electrons would go toward the leaving group and kick the leaving group off. So that would be another elimination reaction, and in that case, you would form the pi bond toward the beta hydrogen that you stole, so here. So those are the 2 possible elimination products that you can make. Now, no matter what base you choose, you will get both of those, but you want to make sure that the major product is the product that you want. Now notice here we have a tetra-substituted carbon. Oops. Or a tetra-substituted double bond. The atoms in the double bond are bonded to 1, 2, 3, 4 carbons, so tetra-substituted. Our other double bond only has 2 carbons bonded to it, so that is disubstituted. The disubstituted one is the less substituted one, that's the Hofmann product. The tetrasubstituted one is the more substituted one, that's the Zaitsev product. And the Zaitsev product is technically more stable. These pi electrons spread out through hyperconjugation into the sp3 orbitals that kind of align, one of which kind of aligns with the p orbitals in the pi bond. And that helps to stabilize the molecule when those electrons spread out. So the Zaitsev product is technically the more stable one. However, you'll notice that we are here trying to get the Hofmann product. And the only way you can get the Hofmann product as the preferred product is by using a bulky base. This is less substituted because it's less crowded. It's in a less crowded area. And so a bulky base that can't wiggle its way close to this other more substituted hydrogen, that will pick off this other hydrogen more often, and that bulky base will create the Hofmann product more. Now, the famous bulky base that you want to be familiar with is potassium tert butoxide, so TBU-OK. And that looks like this. You have the tert butyl group with an oxygen on it that has a full negative charge, and then the potassium is going to stabilize that charge. So the only reagent you would need in order to get this major product, this Hofmann product, would be potassium tert butoxide, TBU-OK. And that will make that elimination reaction happen. Okay, let me minimize that so that we have that there as a record, but we don't want it to confuse our next analysis. All right, C. We see a molecule. In the molecule, we have a pi bond. And so instantly we should think addition as opposed to substitution or elimination. Now, what appears? What are we adding on the molecule? One thing we have in the product that we don't have in the reactant is bromine. So we know we're going to add a bromine. Let's look at the other thing. The other atom in the double bond has 0 hydrogens. This final one has 1 hydrogen. That means that we're also going to be adding a hydrogen. So we need to add H and Br. Well, that's hydrohalogenation. So we know we're going to add HBr. The question is that all we need to add? Is this Markovnikov addition or anti-Markovnikov addition? Because just HBr all by itself is Markovnikov. In other words, the H will go to the less substituted carbon. If you want anti-Markovnikov addition, you'd have to add to that HBr a peroxide. So that would make the addition anti-Markovnikov. So the H there will go to the more substituted carbon. Well, let's look at where the H ended up going, where we want it to go in this reaction. This carbon on the left is bonded to 1, 2, 3 other carbons, so it is tertiary. The carbon on the right is bonded to only 1 other carbon, so it is primary. The hydrogen went on the more substituted carbon. That is anti-Markovnikov. If hydrogen goes to the more substituted carbon, that's anti-Markovnikov. And so we don't just want to add HBr here, we also want to add a peroxide. That's the only way that we would get that anti-Markovnikov addition. And so the answer for this would be HBr and a peroxide. Okay. For D, we see an alkene, we see a pi bond, and so instantly we would think we're doing addition here, as opposed to substitution or elimination. What 2 things have we added? Well, we look for things that are in the product that are not in the reactant. Now, nothing is drawn explicitly, but if you draw the hydrogens in, you'll see that this has 1 hydrogen and no hydrogens on the other carbon, whereas here you have 2 hydrogens and 1 hydrogen on this other carbon. In other words, you've added a hydrogen and a hydrogen. Well, that's hydrogenation. So you'd add H2 gas and platinum, palladium, or nickel. You only have to choose one. I'm going to choose platinum here, but you could just as well choose palladium or nickel. Either of those would work. And that is the recipe that would make this transformation happen. Turns the alkene into an alkane. Okay, E. You see an alkene, a molecule with a pi bond, or a hydrocarbon with a pi bond, and you'd think, okay, we're doing addition reactions here. What are you adding? Well, look for what's different in the product. Here we have a chlorine that's not there in the original product. And draw the hydrogens in on the 2 carbons in the double bond if you ever can't find a second thing. Here, this has just 1 hydrogen. Here, the other carbon has 2. And so we've added 1 hydrogen. Oops. So we've added an H and a Cl. Well, that's hydrohalogenation. So we know we're going to add HCl. The other thing that we want to add, that we want to consider, is whether we have to use a peroxide or not. Now remember, if we do just a hydrogen and a halogen, then we get Markovnikov addition. If we do hydrogen, a halogen, and a peroxide, then we get anti-Markovnikov addition. So what happened here? Where did the hydrogen add? And here I'm going to erase the hydrogen that stays the same just so it doesn't distract us. The carbon that has the hydrogen on it is bonded to 2 other carbons. So that is secondary. Oops, let me actually... Secondary. The carbon that has the chlorine on it is bonded to 3 other carbons. So that is tertiary. The hydrogen added to the less substituted carbon. That is Markovnikov addition, and that means we would not add a peroxide. The final recipe that we would need to add is just HCl. Okay, for this next one, let me just include these notes we have from the previous one. So what we see here is we have an alkene. You look at the reactant, you see a double bond between carbons, and so instantly you should think, okay, what we need to do here is an addition reaction, as opposed to substitution or elimination. Well, what are we adding? Look for things that appear in the product that are not there in the reactant. You have this OH, that wasn't there. Now you might be tempted to say that this methyl group is something because it's coming out now, but watch out, the methyl group really was there. It just wasn't facing toward us. The thing that's there now that wasn't there before is a hydrogen, which is going away from us. This carbon here doesn't have any hydrogens. The carbon on the other side has 1 hydrogen because it only has 3 bonds drawn in explicitly. So we're adding H and OH. Now we have 3 ways of adding H and OH. These are our notes from last time. 3 ways of adding H and OH. The first way was acid-catalyzed hydration. Oops, let me do this in a different color. Acid-catalyzed hydration, that was Markovnikov addition, but we had to watch out for rearrangement. The second way was oxymercuration. Demercuration, that's Markovnikov addition, but you don't get rearrangement. And finally, the third way was hydroboration oxidation. That did anti-Markovnikov addition and syn. Excuse me, syn addition, crucially. So anti-Markovnikov. Well, what type of addition did we have here? Was it Markovnikov or anti-Markovnikov? Markovnikov addition means the hydrogen goes to the less substituted carbon. Anti-Markovnikov addition means hydrogen goes to the more substituted carbon. So the carbon that has the hydrogen on is bound to 1, 2, 3 other carbons. That is tertiary. The carbon that has the OH on it is bonded to 1, 2 other carbons. That is secondary. The hydrogen went to the more substituted carbon. That is anti-Markovnikov, and so you'll want to do hydroboration oxidation. And notice that the stereochemistry of the bonds confirms that. Notice the H and the OH both are going away from us. That means they added to the same side, the same face of the double bond. They could have also added coming out at us, and that's what this En is telling us. That En is the enantiomer. So the only way we can get that syn addition, that syn anti-Markovnikov addition of H and OH is by doing hydroboration oxidation. And so the recipe that we would want to add here would be first, you can bubble some borane gas, BH3. Now you'll want to stabilize that by tetrahydrofuran. The tetrahydrofuran uses its lone pairs to stabilize the empty p orbital on the boron. Now if you don't want to use a toxic gas, you can use a solid like 9BBN, much easier to work with. That's the first step. The second step, so this adds the hydrogen in the boron, that's hydroboration. The second step is to replace the boron with an oxygen, with an OH, and you get that OH from hydrogen peroxide. You have to activate it with sodium hydroxide. So the answer for this exercise is going to be this recipe here. Those 2 steps for hydroboration oxidation. That's how you could get that transformation to happen. Okay, for G, we look at the reactant and we don't see a pi bond, so we're not thinking addition reactions. Instead, we see a bromine. Now that can act as a leaving group, and a leaving group is strongly suggestive of either elimination or substitution. To figure out which one we need to do here, look at the product. Did we replace the bromine with something, or did we just eliminate it from the molecule? We eliminated it from the molecule, and so what we're going to do here is elimination. Now with elimination, you need a leaving group and a base. So we need to add some type of a base. The question is, will it be a skinny base, or a bulky base? With a skinny base, we'll get the Zaitsev product as the major product, and with the bulky base, we'll get the Hofmann product as the major product. The Zaitsev product is the more substituted alkene, and the Hofmann product is the less substituted alkene. Okay, well, let's imagine the two possible products we could get here. If this is our alkane, our haloalkane, the carbon that has the bromine on it is the alpha carbon. Each carbon attached to that is the beta carbon. So we have 3 beta carbons here. Notice these 2 beta carbons on the methyl groups are the same. They're methyl groups attached to the alpha carbon. So they'll give you the same product. I'm just going to consider the one at the bottom. You could have a base that steals a beta hydrogen from the side. The electrons would go toward the leaving group and kick the leaving group off. That's the elimination. And in that case, you would get this product here. You would form a pi bond toward the beta hydrogen that the base stole. So that's one possibility. Another possibility is the beta hydrogen that you take is from the other beta carbon. So this one right here. So if a base came by, if a base came by and steals that hydrogen, the electrons could go toward the leaving group, kick the leaving group off. And in that case, you would have a pi bond forming toward the beta hydrogen that you stole. There. So those are our 2 possible products, depending on which beta hydrogen the base steals. Okay, if we look at those 2 separately, so I'm going to make some more room here, I'll kind of minimize that. If we look at these 2 possible products separately, you'll notice that this one here, this double bond, is the carbons in the double bond on the left are bonded to just 2 carbons, and so that is di-substituted. If you look at the one on the right, the carbons in the double bond are bonded to 1, 2, 3, 4 carbons, and so that is tetra-substituted. The more substituted product is the more stable product, because the pi electrons here can bleed out into one of those sp3 orbitals in more places, 4 places as opposed to just 2, and when the electrons spread out in that way, it stabilizes them. So the tetra-substituted product is the more stable product. That's the Zaitsev product. That's always the major product for an E1 reaction, but in an E2 reaction, it depends on whether the base is skinny or bulky. The less substituted, di-substituted product here is the Hofmann product. Now that's a less stable product technically, but the hydrogen that was stolen was in a less crowded environment. So if you have a bulky base, like potassium tert butoxide, that will steal the beta hydrogen in the less crowded environment and give you the Hofmann product as your major product. Technically, you always get a mixture of these 2 products. If you use a skinny base, and examples of skinny bases are sodium hydroxide, sodium methoxide, or sodium ethoxide. Remember, this is just a CH3, a methyl group, and then the ET is just an ethyl group, so CH2CH3. Those are skinny bases. They can wiggle their way in to this beta hydrogen that's in a more crowded environment and give you the more substituted alkene. Well, notice here what we want is the Zaitsev product. We want the more substituted alkene. And so the reagents that we need to use are any one of these skinny bases. So I'm just going to use sodium ethoxide. You could use sodium hydroxide, sodium methoxide, or sodium ethoxide. Any one would work. And that is the answer for this exercise. So I'm going to make these notes a little smaller so they don't distract us as we solve our next exercise. All right, and this is our last one for this exercise. So we see an alkene, and instantly we should be thinking addition. We're going to be doing addition reactions as opposed to substitution or elimination. What are we adding? Well, look at the product. What's there that's not on the original molecule? We see a bromine. If you don't see a second thing, draw in hydrogens on the atoms in the double bond. So here we have just one hydrogen here. Here we have two. So you'll notice that one of those hydrogens appeared. The second one appeared. It wasn't there before. So we added an H and a Br. Well, that's hydrohalogenation. We'll add HBr. The other thing we have to watch out for, though, is whether we have to add a peroxide to get anti-Markovnikov addition. So remember our notes from above. If you add just HBr, then you get Markovnikov addition. The hydrogen goes to the less substituted carbon. And if you add HBr with a peroxide, you get anti-Markovnikov addition. The hydrogen will go to the more substituted carbon. So I'm going to erase this other hydrogen here that's not reacting. And let's think about what type of carbon the hydrogen is on. So this carbon that has the hydrogen is bound to two other carbons, that is secondary. The other carbon, the one with the bromine on it, that's bonded to 3 other carbons, that is tertiary. So the hydrogen went on the less substituted carbon, and that is Markovnikov addition. So you wouldn't add peroxides here, just the HBr all by itself would be the correct recipe to make this transformation happen. Okay, well these are one-step transformations. We will slowly build our way up to 2, 3, 4, all the way to 10-step transformations in Organic Chemistry 2. But in Organic Chemistry 1, we'll at least get up to 4, maybe even 5 steps in order to get from the reactant to the product. So a crucial thing in order to do these, you could see, is just to have each of the reactions memorized and to know the notes for them. Syn, anti-Markovnikov, things like that. Do you get rearrangement or not? And then once you can recognize that, those details help you to choose between the different reactions, and once you know the reaction, you can write in the recipe that you would have memorized too. And so this hopefully gives you a sense of how you can think through those recipes once you have them memorized. You can analyze the reactant and the product to figure out which recipe you need to use.